All right, type 1 and type 2 errors. There are the important ideas. If you missed them, take a pause. Check your understanding. Mr. Wilcox purchased a trick coin that is supposed to land heads up 75% of the time. So the claim is right there that this coin lands heads up 75% of the time. One of his students volunteered to test this claim. The student flips the coin 50 times and finds that the coin lands heads up 35 times. So that is creating our sample, right? He does a sample. We're creating a p-hat of 35 out of 50. We might not need it, but it's just good practice to make sure we know where this all comes from. The student then performs a test of the following hypotheses at the alpha equals 0.1 significance level. So that's setting up our significance level. So we have our two hypotheses, the null and the alternative. The null being p is 0.75 and the alternative is that p is less than. So because the p-hat 35 over 50 is equal to 0.7. We believe that this is less than 0.75. That part's already done, but just to explain why we're testing if it is less than. But I'm going to get started by just defining each of these like in context of the problem. So the null hypothesis is that p equals 0.75. Essentially, this is saying that the coin works as advertised. So like the store says, running out of room, that it'll land heads 75% of the time. So that means if p is 0.75, it works as it's supposed to. Versus if p is less than 0.75, that means that the coin does not work as it's supposed to, or as advertised. Does not work as advertised. All right, and that's going to help us write our types of error. And here, of course, is our defined parameter. P is the true proportion of tosses. This coin would land heads up. So number 1, describe a type 1 and type 2 error in this setting. Remember, type 1 is where the null is true, but we had rejected the null. And to describe it, I'm going to kind of use what was in the important idea. So the null hypothesis context is true. So I'm going to say, though the coin does work as advertised, we find convincing evidence for the alternative that the coin does not work as advertised. All right, for a type 2, that is where the alternative is true, but we fail to reject the null. So we're going to say, though the coin does not work as advertised, we don't find convincing evidence that it lands heads up less than 75% of the time. Again, I just kind of restated the alternative in a new way, just because We already said it once, so we could add something new to it. All right. So for question 2, which type of error may result in Mr. Wilcox returning the coin and writing a negative review? So in order to determine this, you really want to think about the evidence that was collected, not the truth. Because we're going to assume that he doesn't actually know the truth. Like the truth can let us determine what type of error was made, but we're assuming that he is going based off of just the convincing evidence found. So in type 1, we found convincing evidence that the coin does not work as advertised. Versus in type 2, we don't find convincing evidence that it does not work as advertised. So even though type 1, the coin does actually work, the convincing evidence is telling us it does not. So in a type 1 error, he would most likely return the product and write a negative review because he is convinced that it does not work. Now, question 3, if the student were to use a significance level of 0.05 rather than 0.1, would this make it more or less likely to reject the null hypothesis when the null hypothesis is true? Explain. So if let's say I start with this, right? That the significance level is 0.10. That means between 0 and, let's say from 0 to 10%, we are going to reject the null. This is for this equals 0.1. But if our significance level is 0.05, that means only between 0 and 5% do I reject the null. So as I transition from a 10% to a 5%, is it become more or less likely that I will reject the null? Well, in the first case, from 0 to 10, that is a larger range than from 0 to 5. So it is more likely to reject in the range of 0 to 10 than it is from 0 to 5, simply because there's less values in that interval. So I would say that it becomes less likely. 0 to 5 is smaller than 0 to 10. Good. All right, now as I continue on with practice, as you do these problems, I would recommend that you start with step 1, determining if it is 1 or 2 samples. And then step 2, you want to look for hints that could help you decide your null and alternative hypotheses. So like if you look for conclusions, or if you look for things that, outcomes that we want to happen, or things that people believe. So those are the type of things that can help you write your hypotheses. So I'm going to start with number 1. A medical researcher has tested a new treatment for poison ivy against the traditional. All right, right there. We're testing a new treatment against a traditional one. That is 2 different things going against each other, making this a 2 sample. So those 2 samples being the new treatment and the old. And so anytime you have a 2 sample, it's always really important that you define which is P1 and which is P2. So let me just say I'm going to go new is P1 and old is P2. And if you do it backwards, that's fine too. Doesn't matter. Then it goes on to say with a p-value of 0.047, he concludes the new treatment is more effective. Now, a p-value is not the same as p. So there's 3 things with p's that you need to get straight in your head. We have p, p-hat, and p-value. Make sure that you can define each of these separately and you know what each of them mean. P-value is not p. So when I go to write my hypotheses, my null hypothesis, because this is a two-sample test, my null hypothesis is always the same, and that is that P1 minus P2 equals 0. Essentially, we're saying that P1 is equal to P2. So there's no difference between the two ointments. The alternative hypothesis then, well, that comes from the problem. It tells me that he concludes the new treatment is more effective. Well, if he's concluding the new treatment is more effective, that tells me a few things. First off, that tells me that he has rejected the null, because our null is that there is no difference between the two. If you reject the null, that means you have convincing evidence for the alternative. So you can kind of say that the alternative is true. So that means that this statement right here is the alternative. So the alternative is that the new treatment is more effective. So I'm going to write that here. New is more effective. But what does that look like as our difference equation? So if I do P1 minus P2, and I know that P1 is new and P2 is old, if the new treatment is more effective, that means that the new one, P1, should be larger than P2. So if P1 is bigger than P2, and I do P1 minus P2, I would expect that this would give me a positive value. So I'll say P1 minus P2 is greater than 0. All right, now explain the meaning of the p-value in this context. Okay, so in order to explain what the p-value means, I'm just going to say the p-value, remember, that is the probability of our observed value. So I'm going to say that it is the probability of getting the observed statistic, which is our p-hat. So the probability of getting the observed, well, that is observed statistic was only 0.047 given the null hypothesis that there is no difference in the ointments. So remember, our p-value is the probability of our observed value, but that is under the assumption that the null is true. All right, so which error could have potentially been made? What is the consequence of this error? So what error could have been made? In order to figure this out, we need to decide what conclusion was made. And we already did that, right? Way back up here, we said that he decided to reject the null. So because we reject the null, back up to our chart here, reject the nulls right here, the only type of error that could be made is a type 1 error. So based on our little chart, he must have made a type 1 error. Now, what is a consequence of this error? This could be different things. It kind of depends on, what you see as consequences. One thing that could be a consequence is maybe because in this type 1 error, the null was rejected even though it's true. That means that there is actually no difference in the ointment. Maybe a lot of people spend money to go out and buy this new fancy ointment when really it's no better than the old one. So there's different consequences you could come up with for concluding that the new treatment is better when really the two are just the same. All right, for number 2, Production managers on an assembly line must monitor the output to be sure that the level of defective products remains small. They periodically inspect a random sample of the items produced. If they find a significant increase in the proportion of items that must be rejected, they will halt the assembly process until the problem can be identified and repaired. Now, in this problem, is there one sample or two samples? And in this one, there's actually just one sample. We take a sample from the assembly line and we determine how many pieces are defective. Now, to state my hypotheses, the null hypothesis here, what I'm testing against, is the assumption that basically everything's fine. Like there's no issues in the assembly line, all is well. So I'm going to say that my null hypothesis is everything is fine. There's no problems in the assembly line, nothing that needs to be addressed. The alternative then is that there are problems in the process and that's leading to, so problems in the process making defective product. And you don't have to have these exact words, but something like this. Again, there's not really any numbers in this problem, so we're just kind of talking about it in context of the problem itself. So in this context, what is a type 1 error and what is a consequence of that? So remember, a type 1 error is when we reject the null, but the null is true. So that means that a type 1 error would be that everything is fine, but we find convincing evidence that there are problems in the process. Now, what could be a consequence of this? Well, the company might spend a lot of money to try to fix problems that don't exist. So that could be something that would be a bad consequence of making a type 1 error. Type 2. A type 2 error is when we fail to reject the null, but the alternative is actually true. So this would say that there are problems, but we do not find convincing evidence for these problems. So what could be a consequence of this? Well, clearly there's a problem that we're not addressing. So there is a problem happening, but we have not done anything to fix it. So which type of error would the factory owner consider more serious? Probably I would say a type 2 error. Now, you might consider a type 1 error being worse for the owner just because then he has to spend money that's not necessary. But still, they're selling product that is good. So, like, what's worse for your company? Spending money when you don't need to, or not fixing a problem and then selling a bunch of product that is defective? People no longer trust your company. They don't want to buy your products anymore. People stop buying your products, so you have even less money, and it's a whole cycle. So I think type 2 is worse. Which would be worse for the customer? This one is easy. That is definitely type 2. Type 1 wouldn't really affect the customer at all, but a type 2 would be worse because they're more likely to get a defective product. So their test, it currently uses a 5% level of significance. How would changing to a significance level of 1% affect the probability of a type 1 error occurring? How about a type 2? So the probability of type 1 error, we know, is equal to alpha, our significance level. So if it lowers from 5% to 1%, then that means too that the probability of type 1 error would lower. Now, what about a type 2 error? Well, if a type 1 error lowers, right, this means that it becomes harder for us to reject the null. Well, if it's harder to reject the null, that means it's easier that we don't reject the null, which is increasing the likelihood that we make a type 2 error. So simply because the type 1 error decreases, that leads to an increase in type 2 error. All right, and lastly, question 3. Highway safety engineers test new signs hoping that increased reflectivity will make them more visible to drivers. Volunteers drive through a test course with several of the new and old style signs and rate which kind shows up best. So here, first thing that I would ask is, do you think this is a 1 sample or a 2 sample? And I would say this is a 2 sample because we are testing these 2 signs, the new signs and old. So I'll say new is P1 and old is P2. I guess you can do it in reverse if you want. And it doesn't ask me to state the null, but I'm just going to do it anyway because it helps. So the null hypothesis would be P1 minus P2 equals 0. And essentially there is no difference in the signs. And then the alternative, again, P1 minus P2, but we need to figure this out. So it says we rate which kind show up best. As you read this, even though, well, it does, it says that highway safety engineers test new signs hoping increased reflectivity will make them more visible. So right there, this sentence here, that sets up that we want the new to be better. So if new is better, P1 is larger, P1 minus P2 should be greater than 0. All right. Now, is this a 1-tailed or 2-tailed test? Why? This would be considered a 1-tailed test because we only care about, we care if the new signs are better. So we only care about the side of the new signs being better if the reflectivity has increased. Remember, a 2-tailed test is the not equal to. So that's when I look for, is it better? Is it worse? It could be either. All right, in this context, state the type 1 and type 2 errors. What are the consequences of each? The type 1 is that signs, the new signs are not better. But we find convincing evidence they are. And a type 2 is that signs are better. You could write new there. But we do not find convincing evidence they are. Now, consequences, if the signs are not better, but we find convincing evidence they are, then we spend a lot of money going out and we buy all these new signs and we put them on the roads, and actually they aren't any better. If the signs are better, but we don't find convincing evidence that they are, well, then we miss a chance to put out better signs. Which is a more serious error? I would say here, the more serious would be type 1. I would rather not make a type 1 error, that the signs are not better, but we find convincing evidence that they are, because then again, I'm putting out signs that are not any better. So I would say type 1 seems more serious. Now, which level of significance might you choose and why? Well, if I think that the first type of error, type 1, is more serious, then I want to decrease the probability that I make a type 1 error. So I would choose a smaller significance level in order to decrease the probability of a type 1 error. And last, part D, the engineers hope to base their decision on the reactions of 50 drivers, but tie and budget constraints may force them to cut back to 20. How would this affect the probability of type 1 and type 2 error? Well, if I lower the sample size, we know that this is bad, right? A larger sample size is always better. So if I lower the sample size, that will lead to higher chances for all error, both type 1 and 2, because it just makes our data less accurate.